In this section, we're going to talk about the production of iron through the nucleosynthesis of low mass stars. I'm going to talk about binary stars first. There are as many stars in binary pairs, that is, stars orbiting each other, as there are in single stars. So the sun is a single star, it doesn't have a companion, but just as many are orbiting each other. In this picture, what you can see here is we've got two stars. They are orbiting a point between them. That's this point here, which I'll come back to in a minute. They are orbiting each other like this. And there are about 48% of stars that are like that, just like there are about 48% that are single stars. You have an area around the star that it has influence over that has to do with how gravity works. And what we've got here is this point that's called the Lagrange point. And this point is the point where the gravitational pull from this star is equal to the gravitational pull from this star. So this is where it's completely balanced. And this surface that we can see that's giving these lobes called the Roche lobes, these lobes are basically where the material inside of here belongs to the star. The influence of gravity is strong enough that the stuff that's in here is still basically belonging to this star, and the stuff inside of this lobe is belonging to this star. But this is where gravity is equal, and so at that point, stuff doesn't belong to either star. We call this the Lagrange or Lagrangian point. Now that's important for understanding what happens next. The evolution of a binary star system depends on how close together the stars are. So you can see here I've got two stars. They've got their Roche lobes, and they're nice inside the lobes. There's nothing much overlapping. And so this is what's called a detached binary. But you can also have a system where they end up with one of the stars filling its Roche lobe. That is to say that material from this star is now expanding beyond its own influence and past this point where the gravity is equal. And so as it passes into this region, it's going to get sucked onto this star. And so this is what is called a semi-detached binary. And this is where mass is transferred from this star onto this star. And then we have the contact binary. And this is where the core, that is to say, the place where nuclear fusion is going on, is well separated. But the outer parts of the star are merging together. And so they're actually belong to both stars at the same time. So we have these three different types of binary. And we're going to look at how a detached binary can evolve into a semi-detached binary and possibly even a contact binary. So we've got these widely separated stars. Here I've got a white dwarf, there's the Roche lobes, and there's another star here. They're completely separated. But this star, if it's just a regular sun-like main sequence star, may evolve into something bigger, a red giant, and even an asymptotic giant branch or second red giant branch star. And so what we have is that, well, in this one, there is no transfer of material from this star to this star. When you get to here, the material is expanding beyond the influence of the star, and it's heading into the influence of the white dwarf. And so this material is going to be sucked onto, and you're going to get a transfer of mass from here as the material goes outside of the lobe. We can get all sorts of different interactions, but one of them is another type of supernova. We already talked about how high mass stars, their cores collapse in on themselves and we get supernovae. We can also have a supernova that has to do with a binary system where you've got a white dwarf and a main sequence. But the main sequence star, just a regular star like the sun, when it dies is going to become a red giant. And so what you can have is that the stars that were originally separated, they were detached binary. When it becomes a red giant, the red giant star is now filling its Roche lobe and the material can flow onto the other star. The other star is a white dwarf and it's made of carbon and oxygen. So here I've got a white dwarf star in the middle. I've got a star here that's losing material. It's going past the Roche lobe and falling onto the white dwarf. And it's going to spiral on, and so that's why you get this big disc-like structure. So the white dwarf is accreting material from its companion. And what happens is that as this material is pulled down onto its companion, we get a thermonuclear explosion. And that is what gives us a supernova. Basically, what's happening is that the material is going to do a thermonuclear explosion, and all of the material that's in here is going to fuse and make heavier elements. But all of the material that's in here gets thrown out into space because the explosion is so strong. When you have a massive star that goes supernova, the core left behind is still left behind. It's either a neutron star or a black hole. Whereas in this case, the star that was here in the first place, the white dwarf, that is just going to be obliterated, and all of that material is going to go off into space. And so the carbon and oxygen that were originally part of this star is going to fuse and make iron and silicon, and the iron and silicon is going to go out into space. And this is actually where most of the iron comes from. So when we think about where heavy elements come from, most of the iron in the universe does not come from massive stars that explode. It comes from pairs of low mass stars that explode. We've talked about making elements up through iron. In a previous segment, we talked about how we can do that in high mass stars as we can stick together more and more massive elements. And then in these low mass stars, we're doing the same thing, but it's all exploding outwards. But we're only making up to iron. It's impossible to make things heavier than iron, more massive than iron by fusion without it going wrong very fast, because you're going to have to give it energy. Up until you make iron, fusion is going to produce energy. But once you pass iron, fusion is not going to produce energy, it's going to use energy. And so it's not an effective process. We've made these things that up to iron, 26 protons, it's element number 26, 30 neutrons. But on the Earth, we have stable elements up to uranium. That's element number 92. It has 92 protons, and the most stable element version has 146 neutrons. Okay, so how do we get from having iron made in supernovae, whether that's a core collapse of a massive star or the explosion of a binary pair, how do we get from that to having all the other elements? Well, that's going to be the topic of our next segment.